So we had reflections. Okay, reflection. So we had two questions, max terms and hazard, that you were going to reflect. Let's see what did you put there. So I go in the middle, I select one by random. Chris is here. Chris gone? No? Or maybe he is here or she is here but doesn't raise hand. David? No? Oh, two David. David Olek and David Brunner. Nobody? No, none of them? David, yeah? Okay. Brunner, yeah? Okay. Very good. So that's good. So what did I ask? I asked, when you are going to use max terms, when are you going to use max terms, and when you use min terms for logic minimization. When we use min terms, the final design was an AND OR circuit. What about when we use max terms? Okay, so let's go to David. So David is saying that max terms are useful for cases when the truth table of an expression has less zeros than ones. Yeah. I guess you told me the same thing in the class, so you are good. Instead of using the rows of ones to write an SOP, sum of product, we can use zeros to write SOP, to write POS, okay? Product of sums. SOP of the negation of the expression? Oh, okay, perfect. And then apply a negation to that is using De Morgan's to get a POS. Or you could directly write your POS later. So first, you might need to think of the negation, but later you could directly go there and write your POS, product of sums. If we take the Carnot map of this truth table, the group together zeros are our max terms. What about the circuit? And or and? You didn't write it, yeah? You forgot? Yeah. Okay. So let me tell you something about and or and or and. If we go to, let's say I bring a PowerPoint here. Control P. Okay, so look at here. When we used sum of products, at the final stage we had something like that. For example, if it is three variables A, B, C, then we had A naught here, B naught here, C naught here. So based on our final expression, we had some product terms. The product terms, for example, are like that. A naught B, for example, A naught B plus C naught B naught. Something like that. And then plus that, A naught B naught, and plus that. So we came up with some kind of this circuit. This is AND OR circuit. And if you remember, we talked that you could very easily convert it to a NAND gate. Do you remember? NAND gate. How? Just put a NOT here. So if we put a NOT here, we have to put another NOT to be the same as before. So this is the one, and this is the one. So if we do that, we have NAND here, we have NAND here, and also this is what? This is a NAND. No, this is a NAND. This is the De Morgan-Lewis said the OR of the negated would be NAND. NAND. So we very simply, we could convert our circuit to a NAND circuit. Okay? When we have product of sums, so let me, okay. When we have product of sums, then we have OR and circuit. So it is something like that. For example, A, B, C, and this is A, this is A naught, this is B, this is B naught, and this is C, and this is C naught. Then, for example, we have A plus B plus C, so A plus B plus C. And then we have another product, another sum term, for example, B naught plus C naught, B naught plus C naught. Then we have another term, let's say A naught plus B plus C. And they are AND together. Oh, and. So, very easily, you could change it to a NOR circuit. Is that right? If you put NOT at the output of an OR, so I write it here to not happen that. So this is an OR gate, and it went to an AND gate here. So we had OR gates, and we had AND gate. So if you put a NOT here, and then you put another NOT here to make it the same as before, then you have a NOR gate. A NOR, this is a NOR, this is a NOR, this is a NOR, and this is also a NOR. So you could convert it easily to NOR gate. So sum of products would make a NAND circuit. Product of sums would make a NOR circuit. So you remember that. If you wanted to have a NAND circuit, you go for sum of product. If you want to have a NOR circuit, go for product of sums. Okay. So let's go back to reflection. The next reflection would be hazard. So hazard. It's the question is, what is a static hazard? What kind of glitch does it generate? Okay. So, did you write your reflection? That's right. Yeah. Did you write your reflection? No? Why not? You lose points. So what about you? No? No reflection? Why not? Okay, just this reflection. So the rest one you had written before. Yeah, okay, very good. Okay, what about you? Yeah. Reflection? Okay, so you didn't, or you did? You did reflection? No. Oh, well, too bad. So what about you? Yeah. Yes. Yeah, so the same. You mean you didn't have reflection, huh? Huh? I don't hear you. Oh, you are the first one. What's your name? Let me see which is the first one. Very good. So we could find somebody at the first. So Jin Yuan. Yeah? Jin Yuan. Very good. So it's good. We found somebody. So a static hazard, Jin Yuan wrote, a static hazard is a timing anomaly that can occur in digital circuits. Very good. There are two types of a static hazard. a static 0 and a static 1. A static 0 hazard occurs when the output of a circuit has transitions to logic 0. Yes, a static 0 is something that momentarily has a transition to 1. A static 0. A static 1 is when you expect the output to be 1 and then momentarily goes to 0, come back. So a static 0 is the one that the transition to logic 1, I guess. Yeah. Did you write it from some place or just using the lecture? So I would like to make sure that am I right, or maybe you are right. How did you write it? From YouTube. So maybe I am wrong. But as I remember, a static 1 is something that the output should be 1 and then momentarily goes to 0 and then come back. A static 1 hazard. The same example that I showed you, that was a static 1 hazard. And a static 0 hazard is something that we want the output to be 0, but it goes to 1 and come back. Okay. So I have to find which one is correct. But as I taught you, a static 1 goes to 0, come back. A static 0 go to 1, come back. Okay. Very good. Shinyan. Very good. Okay. So let's go to quiz. Okay? Quiz. So the quiz is here. I will put it here. Why it's not coming down? Okay, I make it just a moment, so I enable it. So quiz setup, availability, it is 11:49, so that's not bad. You have, I guess, how long? 8 minutes, which would be enough. Maybe you will need less. So I put it 11:49. So I put 11:55. 11:54. Okay. Password, no password for the first time. And then you could see your own answer and correct answer. And that's it. Save and close. Okay, start please. The quiz called max term hazard. Max term and hazard, not max term hazard. Okay, next topic. Let's move to next topic. Everybody not finished exam? For bring it down? Okay. Last time we tried something. I don't know if it was good. I don't remember the setup. Is it good?
Yeah, it's good.
It's better, yeah? I wish I could turn off this one. Okay. Is it better? Yeah. If not, please let me know. I could play with this. There is a very complicated device here that I could play with. Okay, everybody here? Let's go to the next topic. Before going to the next topic, I would like to ask you if you have any question regarding the exam. I gave you a sample exam. I gave you problems from chapter 3 of the book. You could see the problems of chapter 1 and chapter 2 of the book also. They are good. You could solve them to have practice, be ready for the exam. Yes.
Would we just find them in the textbook, or are they on the Brightspace for chapter 20?
The questions you mean, the problems?
Yeah, like practical.
Don't you have the book?
Yeah.
You do? If you do, you go to the chapter and the problems are good. So for the practice, they are good. If you don't have the book, I could just provide you the questions like what I did for the chapter 3. In chapter 3, you see here I put in the exam section, in the exam section, I put chapter 3 problems. So I could do chapter 2 and chapter 1 if you don't have the book. If you have the book, then that's okay. You have to. Okay, so if I forgot, just put in the discussion, so I do it. I try to remember for in the night, in the evening, I will do that. But if I forgot, you tell me, I will put. So the exam would be on Tuesday, and it seems that we are going to the building, yeah? You said that we might not go to just be here. I don't know. I am very confused. Because they told me that the exam should take place in the building, that building, so I sent it for you. I tried to ask them before Tuesday, and if I found anything, I will let you know. But up to now, I think the exam is in the building, in the Demaros building, at the corner here, and in the 3rd floor. If not, I will let you know. Have you ever, anybody of you, have you ever had exam there? No? I don't know. I will ask them. I actually asked them. I sent email asking them, okay, should we here or should we there? I don't know. So they will provide, they will reply. Okay, for the exam, what we had binary logic, binary rules. Then we had gate realization, so you could have any kind of function implementing using gates. And then we had logic minimization. So what we covered up to now is this. So any problems that I can give you for designing a circuit, you should be able to do that. For example, we had one example in our class for multiplexer. Do you remember? Multiplexer. So whenever there is a question, a problem asking you to design the circuit, you start from the truth table, try to draw the truth table for that problem, let's say multiplexer, and then for truth table you have inputs, you have output, then you try to use Carnot map to simplify that, or you may use the min terms and try to simplify using Boolean algebra, or max terms and using Boolean algebra. So we had different methods to do that. Okay, so the exam would be something like that. I want you to design a circuit. I will give you a problem like a multiplexer, then you have to design it. So if you want to make practice, do something like that. Go and find the problems that they ask you to do something. This is the main part of the exam. The other part would be some kind of binary calculation and these things that we had covered before. Okay. Now we are going to chapter 5, actually topic 5. In book, I guess it is chapter 4. I am not sure. Yes.
Can we for the lecture just practice on some problems on the
If you had taught it before, yes. But if you don't, so there is no difference.
new chapter after the midterm?
But no, you haven't thought about it. This one is helping you. I will tell you this will give you some idea about solving the design. But if you want, I can do that. It's okay.
Because most of the lectures were just
No, this is something that I asked you that last time. I asked you, okay, go work on these problems, and if you had any questions in the next lecture, we will work on that. But it seems that nobody has done anything, or done anything, and you have no problems. So it's two cases: either you haven't done anything, or you tried to solve and everything was okay, and you don't have questions. Anyhow, if you want, we can do one problem now. So what to do? What problem do you want to do? So let's try a decoder. A decoder. Do you know what is decoder? Have you heard of that? Decoder. You heard decoder, but in our context, what is decoder? Okay. So let's do the decoder. To do that and to not again have the problem as before, I will put some blank slides so I could write on that. Okay, decoder. What is decoder? Decoder, yes, please. Very good. Where did you have this? The lab. Oh, you had done the lab, so you know that. Okay, so this is an example of a problem. I guess you have also designed it in the lab, or no? Not yet. Okay, so let's do it. The decoder is, when we are talking about the binary, do you remember we said we have some kind of coding, for example, BCD, 7-segment coding, ASCII coding, gray coding. Remember that, yeah? Okay. And even binary. Binary is a coding. Binary is a coding. When you write 0, 0, 0, 0, it means something. And what does it mean? It means 0. When you write 0, 1, it means 1. So you are coding. You put a code. This is a code. This is something that represents a concept, which is 1. So in coding, we put codes. In decoding, we would like to reach the main concept from the beginning. For example, you have heard about MP3. MP3 is an encoding standard. It gets a raw audio format, sound, and then it converts it to a compressed bit stream, compressed 0 and 1s, which they represent the original sound. MP3 is a compressed compressed coding of sound. So in encoding, we receive audio and we deliver MP3 file, which will be 0 and 1s. For decoding, we get MP3 file, decoding here, encoding here. For decoding, we get MP3 file. For example, in our computer, we double-click on an MP3 file, so the computer loads the file, then decodes it to the sound, and then plays it through the speakers. So coding and decoding is that. So now the problem is, I want you to design a circuit to receive 2-bit binary number, and it decodes it. So here, decoding means it converts it to 0, 1, 2, 0, 1, 2, 3, because as I told you, 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3. So I wanted to decode it. So for decoding, I put 4 outputs. One of them represents 0, the other one represents 1, the other one represents 2, the other one represents 3. So this circuit has 2 inputs, the binary input, and has 4 outputs. The outputs are the decoded of the binary number. So what does it mean? It means if, for example, I put 0, 1 here, I want the output 2. Output 0, 1 is 2. I want the output 2 to be active. And the rest of the outputs, no active. If I put 1, 1, then the output 3 should be active. And the rest, no. So let's draw the truth table. The first step is defining the problem, and now we can draw the truth table. So the truth table would have 2 inputs and 4 outputs. 2 inputs and 4 outputs. 2 inputs, 4 outputs. 1, 2, 3, 4. So the inputs would be, for example, A0, A1, or AB. It doesn't matter. AB, and the output would be, let's say, output 0, output 1, output 2, output 3. So if we have 4 possible combinations, these are the 4 possible combinations. We have 2 inputs, so we have 0, 0, 0, 1, 1, 0, 1, 1. And now we have to write our outputs. O0 is 1 when the input is 0. And for the rest of the possible combinations, 0. So only for 0, 0, O0 is 1. And for the rest is 0. Okay? O1 is 1 when we have input as 1. And the rest is 0. So the input 1 is this. So O1 is 1 here and 0 for the rest. Okay. O2 is 1 at 2 input. Even input is 2. So input is 2 is this. So O1 is 1 here, O2 is 1 here, and 0 the rest. And O3 is 1 at input 3 and 0 for the rest. Okay. So this is our truth table. We have 4 outputs, so we have to design 4 circuits because we have 4 outputs, and we have 2 inputs. But since it is 2 input, it is very easy. And you could say that when we have only 1, 1, and the other is 0, then it is an AND, very simple min-term solution. Each one of them is a min-term. So O1, we don't need to draw a Carnot map here. But the systematic method is when you had the truth table, especially when it is 3 variables, 4 variables, then you have to draw the Carnot map, and then from the Carnot map find the implicant, and then prime implicant, and then essential prime implicant, as we discussed before. So here it's very easy. O0 would be A0, B0. O1 would be A0, B. O2 would be A, B0, and O3 would be AB. Okay? Very simple. So it is a very simple. And what is the circuit? If you want, we can draw the circuit also. Circuit. So we have 2 inputs. Let me write it vertically is better. We have 2 inputs, A and B, and then we have 4 outputs, and each one of them is an AND. Just it. So, and this is A0, and this is B0. So the first one, O0, was A0, B0. O0. O1 was A0, B. A0, B. This is O1. A2 was A B naught. A B naught. And O3 was AB. Good? Okay, a very good problem. If you have any question, let me know. I could try to solve it, and so you have more readiness for the exam. It's easy. So that's it. That's a very typical problem that you would have in your exam. Okay. Now let's go to the topic 5, which is somehow related to this. In here, we are going, actually in logic minimization, we reviewed logic circuitry, Boolean algebra, min-term, Carnot map, don't care, max term, and timing and hazard. So we talked about these before. Now we are going to talk about combinational circuits, RTL combinational circuits. So what does it mean? And you see here I put this as the gray one, so if we have time I will talk about Verilog a little for you, and it is good to practice Verilog. It makes your life much easier. Instead of doing a schematic and putting gates for your design, you just write one line of code and that's it. So let's see if we have time. Now, why? Why do we go to register transfer level? And what is that? We will talk about that. And here, yes. The same thing that we have before. For example, I gave you a circuit like this. The circuit was a multiplexer. So we had a select, and we have two inputs. So the select is ANDed with one input. So this is one input, and select not ANDed with another input. So if S is 1, then the output, oh, what's that? And they are all together. So when S is 1, then the output is A. And when S is 0, the output is B. Okay? And this is a circuit. I gave you this, and I told you, okay, see this input, ABS, and then this input, 0. Okay. So S is 1, both of the inputs are 1, so the output is 1, because when S is 1, the output is A, so A is 1, Y is 1, okay? And if S becomes 0, again, S is 0, so the output would be B. B is also 1, so it is 1. Is that right? Okay. But this is something that doesn't happen in the reality. In the reality, we have delays. So when S here is 1, then it becomes 0, S becomes 0, then it is not instantaneously this becomes 1. So there are some times that S became 0 here, and this is still 0, didn't become 1. Okay? So consider a time that S became 0, but S naught is still 0. Because there is a delay. This this gate has delay, propagation delay. When it is coming from 1 to 0, the output doesn't become 1 at the same time instantaneously. It takes time, okay? So there is a time, which is about the delay of this gate, where this is 0, so this AND becomes 0, and also this is 0. Both of them are 0, which shouldn't happen at all, because this and up to now, we were thinking when this is 1, this is 0, and when it became 0, this should become 1. But it is not at the same time. It takes time. It has delay. And so this is making our output something else. We should have 1 in our output at the same at all times, because A is 1, B is 1. Either S is 0 or 1, the output should be 1. But when S becomes 0, we were trying to make S 0 to select B to go to output. So we made S 0, but at this time, instead of B going to the output, 0 goes to the output, and it's bad. It is hazard. Yes.
So what's the point then of the circuit if it's always going to be
No, we were expecting it to become 1, to be 1, because you have 2 inputs, both of them are 1, and you designed a multiplexer which is based on select. Either this one should go to output or this one should go to output. Both of them are 1. So whatever S is, it is 0, 1, whatever S is, the output should be 1, because both of our inputs are 1. And this is up before my lecture on hazard. When you saw this circuit, you could say, if S becomes 0, then this goes to output and it is 1. When S is at 1, then this goes to output and it is 1. But I showed you that this doesn't happen in reality, because we have delays. We don't have instant gates without any delay. We have delays. Okay? So this happens.
But like it's selecting, I understand like the delay, it's just it would select the same thing. Like it wouldn't matter if you say 0 or 1 is S, the output's always the same. Like
No, it depends on your application. Let's say, for example, you have an application and you put a switch somewhere. So if you put this switch that side, the output gets from somewhere. If you put it somewhere else, the output goes from somewhere else. So you expect that if you switch this, then the output is this. But this doesn't happen. This output is 1, and when you switch this to 0, the output gets 0 instead of 1. This is hazard. This is a glitch. We have to think about it, and we have to somehow solve. Sometimes it is not important for you at the moment it goes 0 and then come back, because eventually it comes back to 1. So you have 1 there, and it is not very instant for you, so you don't care. Okay, we have hazard, we have a glitch, okay. It goes 0 for 5 nanoseconds, it goes to 0 and then come back, and that's good. That's good for me. For example, you made this switch, and these 2 things will turn a light on or off. The turning off a light on 5 nanoseconds and coming back, your eye doesn't detect. So you don't care. Okay, let's go to 0 and then come back. I don't care. But sometimes you care. If it goes to 0, something bad happens. Like, okay. That's right. That's yes. So the multiplexer is selecting among the inputs that you have which one going to output. And it is a very useful circuit. It is a very useful. You will see maybe in our lab we have something, or in your project you need a multiplexer. Okay, so yes.
We have three selector multiplexer. How do we decide which input
How do?
what input we take into consideration?
What do you mean?
Like when the multiplexer is with the three selector.
The S is selector. Okay.
Yes, three of them. When
Three?
we have multiplexer with three of them.
Three inputs.
Three selectors.
Three selector. Why three selector? Selector just selects between one of them. If you have two inputs, then a bit 8 inputs. Then you have 3 bit. Then you have 3-bit selector.
Which inputs is to take?
Based on your select. So a multiplexer with 8 inputs is something like that. Let me draw it for you. So this is a multiplexer with 8 inputs. So the inputs are, let's say, I0 to I7. And the output is O, but you have now 3-bit selector. So you have S0, S1, and S2. So in this case, we have how many inputs for our design, for our truth table? 1, 2, 3, 8, 11 inputs we have, and we have 1 output. Okay? So if I want to draw the truth table for this, I have to put a table with 2 to the 11, which is 2048 rows. So you have to build a 2048 rows truth table, and the kernel map has 11 variables, so we cannot handle it. And that was a very good question for our topic now. Exactly this question is the main reason for our topic, combinational components. What do we want to do here? We would like to say, okay, you would have some components like multiplexer, like decoder, like adder, like subtractor. These are the components that you will use it in your design, okay? It is not good for each one of them, when gets higher inputs, go to the truth table and try to do it from the beginning. So we should have some kind of a bag. A bag is here. In our bag, we have a 2-to-1 multiplexer in our bag. We have already designed it with the things that we learned in topic 4, okay? We designed it. It was very easy. This was the circuit. Where was that? I don't know. I had it here. Where was it? I don't know. It was there. It was just 2 AND gate and 1 OR gate. Yeah? And in our bag, we have a multiplexer of 2-to-1. Why don't I use this to build this one? This is the idea of combinational components. We have components, we use them to build something bigger. And this, we call it RT level, register transfer level, not gate level. In the previous section, we were just using gate level. Whatever design you wanted, we start from truth table, then kernel map, then minimization, then realization, circuit realization. And it was very straightforward. But it is good for something small. When it gets larger and larger, we cannot do that. Could you be able to do kernel map with even 6 variables, 6 variables is hard, is possible, but 7 variables, no, I don't think we can do that. And 8, 9, here we have 11 variables. So your question is very good, is that it forces us to go to some kind of thinking of components. We have a bag, we go to the bag, and we say, I need a multiplexer, and in my bag I had already a multiplexer, 2-to-1 multiplexer. I bring it and use it to build this. We will see that. One of the things, I guess, multiplexer is here, yeah? Here, yeah. So we will talk about multiplexer, we will talk about decoder, we will talk about parity, we will talk about comparator, we will talk about adder, and then ALU. So these things we are going to talk in here as a combinational component. What is combinational? Why do I say combinational? Do you know? What is the alternative of combinational? Okay, but what is the alternative? If it is not combinational, what is it? No. Integrated? No. We will see. In our next chapter would be that. We have two kinds of circuits, digital circuits. Combinational and sequential. Combinational and sequential. In sequential circuits, the output is not only dependent on the inputs, also to the state or memory of the system. The system has some kind of memory. So in the sequential circuits, we have some kind of memory. So here in combinational, this is a combinational circuit. If you change the input, the output it changes. The output is dependent only on the inputs, nothing else. His input is 0, 0, the output is 0. His input is 0, 1, the output is 0. So on. So, but in a sequential circuit, you have input, for example, you change it 1, 1, and 2 seconds ago, when you have input of 1, 1, the output was 1. But now you put 1, 1 as the input and the output is 0. And it is okay, because the output dependent on the inputs plus the state of the circuit. The circuit has some kind of state, some kind of memory to keep it. So we will talk about sequential later. Now we are in combinational, because we learned about combinational, and, or, not, XOR, NOR, NAND. These are combinationals. So you change input, the output changes for sure. And the output is based only on the inputs, nothing else. Okay? So this section, let me show you. This section, I called it RTL combinational components. So they are components, they are combinational, and they are RTL. It means register transfer level. I guess at the beginning of our course, I showed you a slide of the levels: transistor level, gate level, RT level, and system level. I will show you again. Okay? So very good. Your question, it showed you that you have questions that it needs an answer in this chapter. The philosophy of this chapter is to address these questions. Okay. So let me give my example. So your example was very good, as 8 inputs multiplexer. My example is this. Let's see. Is this. You want to design a circuit which calculates absolute value. Absolute value, you know absolute value. So if the input is 3, a positive number, the output is 3. If the input is -3, the output would be 3, the absolute value of that. we would like to design a circuit which calculates the absolute value. This is our goal. So what to do? So if you want to do, and it has 8 inputs, 8 inputs, 8 outputs. So if it is 3, then the output is 3. If it is minus 3, the output is 3. So for example, this one. Oh, this one is a negative number. You see the sign is 1. This one is 1. So what is this number? Let me 2's complement it. So to make it 2's complement, we start from right. We keep 0, we keep 1, and then invert everything. 1, 1, 0, 0, 1, 0. So this is the negative of this. And what is this? 2 plus 4 plus 8 is 14, 16, 32, 64. 64 plus 14 is 78. So this is 78, and this is minus 78. Okay? I want a design to accept this, and the output should be this, 78. Minus 78 as input, output 78, plus 78 as the output. Okay? So how do we do that? What we have learned in the previous chapter, in the previous topic, we build truth table. We build the truth table. Okay? We have 8 inputs, 8 outputs. We build the truth table. Okay, let's do it. This is the truth table. So we have 8 inputs and we have 8 outputs. And if you look at this truth table, the first half of the truth table, which A7 is 0, the output is exactly the same because it is positive. And then the second half of the table, where the A7 is 1, then the output is something else. Okay? Yeah. If you have questions, ask me. Yes? So you have to think of everything. This one, what is this one number? So you get the positive number. So this is minus 3. So the output is this, 0, 0, 0, 0, 0, 0, 0, 1. This is minus 2. So the output is 0, 0, 0, 0, 1, 0. This is minus 1. So the output is 1. Okay? So we have a truth table with how many rows? 8 inputs. How many rows? Yeah. 256 rows. And if you want to make a car, and you have to have 8 outputs, so you have to simplify 8 functions. And a Carnot map would be difficult, really. 8 variable Carnot map is difficult. So what to do? What do you suggest? How to design this? Absolute value. Could it be something simpler than this? Absolute value. What do you do for finding the absolute value?
See if there's a 1 at the end. And if there is, just take the 2's complement.
Perfect. And if it is not?
Then just hammer output input.
Perfect. So instead of going to this kind of solution, we are thinking of using some kind of other components, which is, for example, tooth complementing. Which is, for tooth complementing also, what do we need? We invert it and then, well, how to? Plus 1. So we need an adder, a component which is adder. And I go to my bag. Oh, there is an adder there. I take it, bring it here, plus 1, invert it, and then, because invert is easy. Invert is just this. So each input goes to this and gets the invert. And then I have to add 1 to this. Okay? So this is RT level, register transfer level. I will talk about register more later. For now, it's enough. Just you had an idea that we have some kind of component which performs a function. Add, comparator, absolute value, something like that. Okay, so exactly, you guessed very good. So instead of that, we go for this is very hard. 8 variable Carnot map, and you have 8 output. So you have 8 variable Carnot map. So we don't go there. We don't go this way. So what to do? Exactly what you told. How do we make absolute value? We use a multiplexer. The multiplexer that we talked about right now, the multiplexer selects based on the sign. If the sign is positive, then the input goes to output. This is a multiplexer. You see how multiplexer is going to be used here. And if the sign is negative, the input is inverted and then added to 1. Okay, this is the design. Okay, let's see. Here is exactly the system. So you look at this. So we have a multiplexer here. The multiplexer is 2 to 1 actually, but 8 bits. An 8-bit number, so it is a 1-bit selector, either that 8-bit or that 8-bit. We have 2 8-bits, 1 and 2, or better 0 and 1. These are 0 selection, this is 1 selection. Depending on S, the output gets one of these 2 sets, these 2 bits, these 2 bits. And the selector is the sign bit, yeah? So we connect A7, A7 is here. So we connect A7 to the selector. A7 goes to the selector. Based on A7, we either select the input, so the input goes to the output. If A7 is 0, then that's it. The output is the same. But if A0 is 1, then we get the inverted of input, and then we have an adder, we plus it, we add 1 to it, and the output goes there. See how simple became? Because we used RT level. We didn't go to gate level to design everything as the gate level. We had some kind of component. Again, this is a component that we have to talk about this. What is +1 component? This is a multiplexer which we have already talked about it for 2 to 1. This is 2 to 1 actually. 8 of them. 8 multiplexer, 2 to 1. It is different than what you mentioned, 8 to selecting one of 8 going out. That is 8 inputs as the multiplexer. But here we have 2 inputs, but 8 2 inputs multiplexer. Okay? Good. So this is our topic today. This in number 5. So this is the slide that we had seen it before. Here in around 1970s, we were using transistors to build our circuit. Then we saw that it's becoming hard. The circuit is becoming larger. So we couldn't come up with transistors. So instead of transistor, we used the transistors to make gates. And then we tried to use the gates to build our circuit. Later, it became harder, that the circuit became larger. So instead of using gates, we used RT, resistor transfer level. So we used some components to build our circuit. And later, again, the circuit became larger and larger. The system gets more complicated. For example, now we have a MP3 encoder, as I mentioned for you. MP3 encoder is a very complex system. So if you want to build a circuit to do MP3 encoder, it is some kind of system level. You need different tools for that. In our course, we will talk about this. We will talk about this in two sections. First section, combinational section. Then we go to the sequential section. Okay? So this is how we are going to work on the register transfer level. So it is some kind of higher level than gate level, but lower level compared to system level. Yes, one level upper. It is some kind of a functional level. Okay. You have no questions, no? You have questions together. Listen to me. Okay. Function. We have functions here. Add, subtract, absolute value. So many things that I've shown you. Okay. Let's look at this system. This is a CPU processor, like Pentium. A simple schematic, not a schematic, not a very complicated, detailed section version. In a processor, you have different components here. For example, we have something which operates arithmetic and logic operations, like add, and, or. These things will be done here. ALU, arithmetic logic unit. Okay, this is something that, and it is combinational. It is just add. You can use gates like and, or, nor, XOR to make an adder. So this is combinational. We have something here which they are registers. Memory, some kind of memory they have, and these are also in our processor. We have something here which I call the bus. You have heard about bus, yeah? Did you? No? Bus, data bus, address bus. So the bus is something that will connect them together. So you calculate something in ALU, then you need to go and store it in register, for example. So the bus takes them and transfers them somewhere else. So we have something for communication, the bus. And also, which is not here in this figure, so maybe in the next slide, we have something to control everything. When ALU does addition, when ALU does OR, does and so on. So there are different components in this complex design. What we are talking in this chapter is this part mainly, the combinational part, the part which calculates arithmetic, logic, like I told you, comparator, absolute value, decoder. These things we will talk about in our chapter. So this is some kind of register, so we will not talk about this. This is a sequential component. We will talk about this in the next chapter. And we have something as to control everything. It has some kind of timing. At this time, do this, then do this, do this. So it has a timing, and the timing controls everything. Says, for example, ALU, now you do addition, and ALU does the addition, gets the result. Now ALU pass your result to the bus. Now bus, go take the result and put it in the storage. Now this is the control things which has some kind of clock, timing, and then putting some kind of control signals everywhere to the things know what to do. So this is the simple schematic, a simple block diagram of a design. And as I told you, we are talking about combinational parts, not the controller, not the storage right now. Later, we will talk about this later. So here we have something which works on data, and here we have something which controls the operation. In the design, in a design, we can say the design has data path and the controller. In data path, we try to work on the data, add, and, or something like that. And in controller, we have controller. And complete RT level digital circuit has data path and controller. And this is like a complete RT level circuit, data path and controller. And control signals go everywhere to the data path to say to data path, okay, now you do this. Now you, for example, if even it has so many operations like ALU has add, subtract, and, or, control says you do add, you do or whatever it says. So we talked about RTL components. Yes.
In the previous slide, on it says CLK at the bottom left. What is
Clock.
that? Oh, clock. Okay.
Clock. So we will talk about sequential circuits, and in sequential circuit, we will later have some kind of synchronous design. Synchronous. In synchronous design, you have a clock. Clock is something like that, okay? Not like that, very straight, not this kind of line. Everything is synchronized with the rising edge of the clock. So the controller at the rising edge of the clock says, do this, at the rising edge of the clock. So it has a clock. The controller in the clock, in the rising edge, calculates what it should be done. Then it generates control signals to the data path. This is how it works. Oh, okay, we have out of time. So we started our next chapter also, but as you could see, this is exactly a continuation of our previous chapter. We talked about circuit design. In that case, we had smaller designs. Now we would like to go to a component-based design. Thank you very much. Have a good day.